This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll examine several illustrated examples of series parallel DC circuit analysis. This lecture operates under the presumption the viewer has more than a passing familiarity with both series and parallel DC circuit properties, including Kirchhoff's voltage law and Kirchhoff's current law. If you lack this requisite level of familiarity with these topics, please review the supporting material at the Big Bad Tech channel and return to this lecture when you are so qualified. Mastery of series parallel DC circuit analysis necessitates active participation on your part, and as such, I may encourage you to please pause the lecture when asked to do so and attempt the example problems on your own. If the answers do not match those illustrated, by all means feel free to rewind the lecture and correct any mistakes you may have made. For our first illustrated example, we're being asked to solve for the voltage drop across each resistor in the system, the current through each resistor. Additionally, we're being asked to solve for VA with respect to ground, VB with respect to ground, and VC with respect to ground. Finally, we're being asked to solve for the voltage VBC. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. A Kirchhoff's current law analysis demonstrates that source current immediately splits into two paths. Let's call the path on the left I single prime and the path on the right I double prime. Source current therefore equals I single prime plus I double prime. If we look at path I single prime, it can be said I1 equals I2. R1 and R2 are undoubtedly in series with one another. If we look at path I double prime, it can be said I double prime equals I3, which equals I4. R3 and R4 are undoubtedly in series with one another. A Kirchhoff's voltage law analysis of the loop in red demonstrates that E equals V1 plus V2. A Kirchhoff's voltage law analysis of the loop in orange demonstrates that E equals V3 plus V4. Finally, a Kirchhoff's voltage law analysis of the loop in yellow demonstrates that V2 plus V1 equals V3 plus V4. These analyses imply that R1 is in series with R2, a simplification I'm calling R single prime that happens to have a value of 1,380 ohms. Additionally, these analyses imply that R3 is in series with R4, a simplification I'm calling R double prime that happens to have a value of 1,180 ohms. This is a pure parallel circuit, and as a result, E equals V single prime, which equals V double prime, and they all equal 41 volts. A Kirchhoff's current law analysis of the pure parallel simplification demonstrates that source current equals I single prime plus I double prime. An application of Ohm's law demonstrates that I single prime is 29.7 milliamperes. Similarly, another application of Ohm's law demonstrates that I double prime is equal to 34.7 milliamperes. Source current equals I single prime plus I double prime. Substituting our calculated values demonstrates that source current is 64.5 milliamperes. Let's now examine voltage distribution within the I single prime path. Current through elements in series is the same. I single prime equals I1, which equals I2, which equals 29.7 milliamperes. An application of Ohm's law demonstrates that V1 is 14 volts. An algebraic rearrangement of the Kirchhoff's voltage law equation demonstrates that V2 is the remaining 27 volts. As a means of checking our work, another application of Ohm's law similarly demonstrates that V2 is 27 volts. Let's now examine voltage distribution within the I double prime path. We could use similar techniques. However, this is also a perfect setup for the voltage divider rule. From A to ground is a known differential of 41 volts, and R3 and R4 are known resistors. An application of the voltage divider rule demonstrates that V3 is 21.5 volts. An algebraic rearrangement of the Kirchhoff's voltage law equation solving for unknown voltage V4 demonstrates that V4 is the remaining 19.5 volts. As a means of checking our work, another application of Ohm's law similarly demonstrates that V4 is 19.5 volts. All we need to do now is determine nodal voltages. Starting at ground and traveling to node A, we experience a 41 volt rise. VA with respect to ground is undoubtedly 41 volts. From A to B, we experience a 14 volt drop. With respect to ground, we have experienced a 41 volt rise, less a 14 volt drop. As a result, VB with respect to ground is 27 volts. Similarly, from A to C, we experience a 21.5 volt drop. Traveling from ground, we experience a 41 volt rise, less a 21.5 volt drop, and as a result, VC is 19.5 volts. VB with respect to C is VB minus VC. 27 minus 19.5 volts demonstrates that VBC is 7.5 volts. Alright, let's move on to our next illustrated example. Our next illustrated example features a series parallel combination of 4 elements. We're being asked to solve for the voltage drop across each element, the current through each element, and the source current. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Let's start with the Kirchhoff's current law analysis of this series parallel circuit. Source current immediately splits into 2 paths, one through resistor R1, one through resistor R2. It can be said source current equals I1 plus I2. Source current recombines and then immediately splits again. One path through R3, another path through R4. It can be said source current equals I3 plus I4. Ultimately, source current equals I1 plus I2, which equals I3 plus I4. A Kirchhoff's voltage law analysis of the loop in red demonstrates that E equals V1 plus V3. Similarly, a Kirchhoff's voltage law analysis of this loop in orange demonstrates that E equals V2 plus V4. Similarly, a Kirchhoff's voltage law analysis of these loops in yellow and green demonstrates that V1 equals V2 and V3 equals V4. These analyses imply that R1 is in parallel with R2, a simplification I'm calling R single prime, where R single prime has a value of 159.5 ohms. These analyses additionally imply that R3 is in parallel with R4, a simplification I'm calling R double prime, where R double prime has a value of 229.2 ohms. R single prime and R double prime are perfectly in series with one another. A Kirchhoff's voltage law analysis of the simplified series circuit demonstrates that E equals V single prime plus V double prime. A Kirchhoff's current law analysis of the series simplification demonstrates that source current equals I single prime, which equals I double prime. An application of the voltage divider rule demonstrates that V single prime is 24.6 volts. An algebraic manipulation of the Kirchhoff's voltage law equation for the series circuit simplification demonstrates that V double prime is the remaining 35.4 volts. Let's examine the electrical properties of R single prime. R single prime is the parallel combination of R1 and R2. Voltage across elements in parallel is the same. V single prime equals V1, which equals V2, and they both equal 24.6 volts. An application of Ohm's law demonstrates that I1 is 91.2 milliamperes. Another application of Ohm's law demonstrates that I2 is 63.1 milliamperes. An application of the Kirchhoff's current law equation for this series parallel circuit demonstrates that source current is equal to I1 plus I2. Substituting our calculated values yields 154.4 milliamperes for source current. Let's now examine the electrical properties of a simplification R double prime. R double prime is the parallel combination of R3 and R4. Voltage across elements in parallel is the same. V double prime equals V3, which equals V4, and they both equal 35.4 volts. We could go ahead and use another application of Ohm's law to solve for I3 and I4. However, this is a perfect setup for the current divider rule. We have a parallel combination of 2 known resistors, and we know incoming current. An application of the current divider rule solving for I3 demonstrates that I3 is 107.2 milliamperes. A rearrangement of the Kirchhoff's current law equation solving for unknown current I4 demonstrates that I4 is the remaining 47.2 milliamperes. As a means of checking our work, an application of Ohm's law demonstrates that I4 is also 47.2 milliamperes. I've got a reasonable degree of confidence our answers are correct. As a bonus challenge problem, consider our original series parallel circuit incorporating these 2 fundamental changes. A 0 ohm short around resistor R2, and finally a misconnection such that R3 is opened. As an exercise to the viewer, I invite you to solve for the voltage drop across each element, the current through each element, and the source current for this modified system. You will note the incorporation of the short and open has fundamentally changed this nature of the circuit. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. A short in a parallel combination shorts out the entire parallel combination. By shorting out resistor R2, we've effectively shorted out the parallel combination of both R1 and R2. As such, current travels through the 0 ohm short and bypasses resistor R1 and R2, effectively removing them from consideration. With R3 open, no current travels through R3. As such, all current travels through R4. R4 experiences a 60-volt drop, and as such draws 800 milliamperes of current. Being the only element in the system, source current is also 800 milliamperes. All right, let's move on to our next illustrated example.